I'm, of course, happy to be here, and this has been a very fantastic workshop. I'm always enthusiastic to come to this workshop. It's very focused, and it's just always of such interest, and there have been a lot of high-quality talks and presentations made this week, and I just hope that Can you hear me now? No. I just hope that my talk does not ruin the quality of the previous talks. Are we better now? Okay. Okay, I have too much altitude. Okay, I get it. But what I'm going to present today is a very narrow slice of the work that Mahesh Kavalakam, Steve Miller, Larry Thomason, and I have been doing over the past couple years, mainly focusing on inferring particle size distributions from SAGE extinction spectra with a specific application to the Hunga-Tonga eruption, which will be presented in the second half of the talk. Now, brief background of Hunga-Tonga before we even get started here is it erupted in January of 22. It had a relatively modest SO2 injection of about 0.5 teragrams. It had a massive injection of water vapor, though, that accounts for about 5 to 10% of the stratospheric water budget, put into the atmosphere within just a few hours. So this is a major eruption. It was also a particularly violent eruption. It threw material all the way up to 55, 60 kilometers. I know Ghassan Taha has a paper in GRL that demonstrates this from OMPS. And it has been assigned a volcanic explosivity index of 6, which is pretty massive. And a lot of people have been comparing this to the 1883 eruption of Krakatoa, just as far as its explosiveness goes. We see a time series of the 1 micron extinction coefficient from SAGE, altitude versus time. We certainly see enhanced extinction beginning in about March of 2022, and that persists throughout the rest of the year. Now, the ups and downs you see here are just because of the latitudinal variation in the ISS orbit, and we're not seeing extremely high extinctions here, but we're seeing things that are certainly significantly different from background. If we look at this plot in a slightly different way, this is the 0.5 to 1 micron extinction ratio. This gives us a very rough gauge as to the size of these particles. Generally speaking, if the extinction ratio is small, then we have large particles, or if it's big, then we have small particles. It's an inverted relationship. So what we see throughout the majority of this enhanced layer here is a small extinction ratio, which indicates that these particles are in fact big. We just don't know how big they are. So the question is, of course, what are the microphysical parameters or size distributions of these particles? But before we get there, I have to give you a little background on the methodology that we use, and this will set the stage so that you can interpret and appreciate the results that will be shown in the second half of the talk. So we presented this to do this as part of the SAGE science team, and within that proposal, we proposed to use me theory to derive particle size distribution parameters, or PSD parameters as I'll call them throughout the talk. And in this, we would account for measurement uncertainty in the SAGE product. We would also provide confidence intervals for these PSD products. We'd expand this to include other parameters such as surface area density or volume density and effective radius. And we would also expand this to include potential bimodal solutions. And I'm happy to say that as of today, all of this work has been completed, at least the algorithm has been completed. We haven't evaluated everything as far as science goes, but all these objectives have been met. I won't address all these objectives in this talk. I'm happy to discuss that offline, but all these objectives have been met. So in doing this, we invoked the standard me theory assumptions that all particles are spherical, the distributions are single mode log normal, unless we're looking at bimodal solutions. Particles are composed of 75% sulfuric acid using the Palmer and Williams refractive indices. And using these assumptions, we built a series of lookup tables of extinction coefficients. So these are nothing more or less than simple three-dimensional NumPy arrays where we have extinction coefficient as a function of mode radius, wavelength, and of course distribution width. And we tested this analysis for a series of extinction ratio combinations. So shown here, we looked at 16 different extinction ratio combinations. I just give them a condition number, starting from 0, of course, because that's where we start counting. And then the first column is our numerator channels, and then the second column or third column is our denominator channels. So you see that some of these conditions only involved one extinction ratio, such as condition 0 here. This is just the 1/2 to 1 micron ratio, but some of them involved multiple ratios, such as condition 5 that actually used 6 different extinction ratios. So this is operating in multi-dimensional space. So you might be asking yourself, why use extinction ratios? We already have the extinction coefficient calculated. Why make this extra step? And it's because the atmosphere simply does not have static number density as far as the particle number density goes. Therefore, this throws off everything. And whenever you calculate extinction ratio, the number density drops out of that term, makes this a much more manageable situation. So how we use these extinction ratios is shown, for example, in this plot. Here we only have 2 extinction ratios, one plotted against the other here. For some of those conditions we just saw, we would do this in 6-dimensional space, but here we only have 2 dimensions because the screen is, of course, only 2 dimensions. But this plot is composed of that lookup table data, and it's composed of a multitude of black dots, but there are so many you can't see in between them. But in theory, what we should be able to do, if SAGE had no measurement uncertainty, we should be able to plop a SAGE observation right in the middle of this plot and then find the closest match between the red dot, which represents our SAGE value, and the black dot, which is our lookup table values. And in theory, we should be able to say this black dot matches SAGE the best, and we know what the PSD values of this black dot is. Therefore, the atmosphere had these PSD values where SAGE was measuring. But the problem with that method is the SAGE does have measurement uncertainty, shown here in our red lines, which means in reality, all of the black dots within the bounds of our measurement uncertainty are potential solutions. Some have a higher probability of being a solution, but they all remain potential solutions in the end. So the question then becomes, well, which one of these solutions is the right solution? And if we can't answer that, which one is at least the best solution? So what we do is we calculate weighted statistics. The weights are assigned based upon the distance between the central SAGE dot and the lookup table values. And we use a multivariate normal distribution that allows us to operate in multidimensional space very easily. And using that, we calculate weighted statistics such as the weighted mean, the weighted median, standard deviation, so on and so forth. So the question then is, how well does that work? To evaluate that, we carried out a series of sensitivity studies to basically determine how well the output value matches the input value. So if we pull values from our lookup table, how accurate are those values of the output model based on what was input? And we evaluate this under 2 scenarios. One, where we get the composition correct, which is an unlikely scenario, and 2, where we get the composition incorrect, which is far more likely. So what I mean by this is we take our imaginary atmosphere, and here we have our lookup table represented by this block, and here we assume that the atmosphere has 75% sulfuric acid. It could have been anything, but we just picked this value. We extract a extinction spectrum from that lookup table. We impose some measurement uncertainty on that value, and then we run it through our solution algorithm that assumes that the atmosphere has 75% sulfuric acid. So our lookup tables here are matching, so we're getting the composition correct. And keep in mind, this is all theoretical work. And from there, we extract our weighted statistics and do a comparison. The results of that analysis are shown here, and here I've plotted the inferred mode radius divided by the target or the true value. So if the ratio is greater than 1, then we're overestimating, less than 1, then we're underestimating. And this was done for an imposed uncertainty of 50%. So this is quite high. It's not unrealistic to see errors that large in the SAGE data. Most of the data is smaller than that, but this is still a realistic value. And what's presented in this plot is the red lines are the weighted median values, and then the bars, as you might expect, are the first and third quartiles, and then the whiskers extend from the 5th percentile to the 95th percentile. So this is representative of the distribution of the solutions within our solution space here. In general, on median, the results are pretty good. So for example, if we infer a mode radius of 200 nanometers, then on median, we're at about 40% overestimated. And this is with a 50% uncertainty imposed on our extinction spectra. If we narrow down that uncertainty to 20%, you see everything comes closer to that 1-to-1 line, so we're getting better. And certainly whenever we infer larger mode radii, like 200 nanometers and above, we're very close to that 1-to-1 line. And finally, whenever the imposed uncertainty is only 5%, we're much closer to that 1 value even then. And you please notice that the Y scale on this plot is adjusted compared to these because the values are so much closer. It's not unrealistic for SAGE to have 5% uncertainty. Again, this isn't where most of the data are, but this is certainly a realistic condition. Now, looking at the effective radius, this is perhaps a better representation of the overall performance of the model, and we see that generally speaking, the performance is better as compared to the mode radius. We're getting much closer to that 1-to-1 line. The y-axis doesn't extend quite as far as it did for the mode radius on the top panels. And again, as we go to these smaller uncertainties, we're getting much closer to this 1-to-1 line. So the take-home message of that is that the PSD estimates are roughly larger, generally larger than the target values, and that the higher moments have better agreement. But what if we get the composition incorrect? We make the incorrect assumptions about the composition. So here, we repeat the same procedure, but here we're assuming that we have something that's not 75% sulfuric acid. It could be anything. We extract our extinction spectrum, impose our uncertainty, and then we run it through the algorithm, making the assumption that the composition is 75% sulfuric acid. So now we have mismatched lookup tables. So how well does that perform? We pull our weighted statistics out of that. And what I want to do here, and this is important, is I want to reference the results of the next slides to what we just saw on the previous slide. So basically what this is going to tell us is how much worse getting the composition wrong is than getting it correct. How much does this impact our results? So what I mean by that is we're going to take this procedure with our mismatched lookup tables, get our statistics, call those S1, and we're going to look at what the results where we had the composition correct. We get those statistics, call those S2, and then what's on the y-axis for the subsequent plots is just the ratio of S1 to S2. This tells us nothing more than how much getting the composition wrong changes our results as compared to getting it right. So shown here, this is making this is setting the atmosphere to 65% sulfuric acid, whereas our algorithm assumes a 75% sulfuric acid. And generally we see that the agreement is pretty good. We're within 5%. On median, we're within about 2.5%. So we're not seeing a substantial difference by getting the composition incorrect. Change it to a 70% sulfuric acid atmosphere, the agreement becomes even better. This makes sense because we're getting closer to the 75% that is in the algorithm. And then going over at 80%, the agreement is still good, but we're now overestimating by just a little bit. Looking at our effective radii, here we see that, again, this is a better predictor. You notice the difference in scales between the effective radius plots and the mode radius plots. Here we have an extent of basically plus minus 1 or 2%. So these are very tightly grouped. So in general, there's almost no difference between getting the composition incorrect as opposed to getting it correct. However, what if we actually have smoke in the atmosphere? There's been a lot of pyro-CB activity over the time of the SAGE, over the lifetime of the SAGE instrument. So what happens if we actually have smoke, but we assume that there's no smoke? So here I repeated the model, and we assume that the smoke composition is 100% brown carbon, no black carbon present. And generally, whenever we have a small mode radius estimate of less than 100 nanometers, the agreement is quite poor. So we're getting a factor of 2 to 3 higher than what we did whenever we got the composition correct. However, we don't expect to have particles that small under smoky conditions. Most of the time, I think that the smoke particles are somewhere right about here at about 150 nanometers, maybe as high as 200 nanometers, but not below 100. Likewise, whenever we estimate that the sizes are very large, we get a lot more spread in the data, but we don't expect to see smoke particles that big. Most of the time, we expect to be somewhere right about in here. But if anyone knows of any observations of smoke that big or that small, please let me know. If we increase the black carbon content to 5%, we see very little difference in the performance. There are subtle differences between these plots, but it's very, very similar. And further increasing the black carbon content to 10%, again, very little difference in the performance. So the black carbon content doesn't appear to be influencing the performance of this model at all, or I should say to any substantial degree. Looking at our effective radius, this is a bit of change of pace because the effective radius is behaving very similar to the mode radius at the small particle sizes, but again, we don't expect to see particles that small in smoke. But whenever we get to these larger particles, we're observing overall better performance, and certainly whenever we get to the 400 to 500 nanometer range. So, in general, if smoke is small, which we don't really expect, then the estimates are significantly impacted, though larger smoke seems to be less impacted. Larger smoke seems to have less influence on the results. So, in general, the PSD estimates that we retrieve are about 25% too high. Getting the sulfuric acid content wrong generally has a minimal impact. That's something that we can disregard for right now. This is a secondary impact. If we're arguing over a change of about 2 to 3%, then I think we can declare victory. That's not something we need to worry about. And failing to account for smoke might have a substantial impact if the particles are in fact small, but otherwise it is expected to have a relatively minimal impact. So with that, I offer apologies for the extended background. I hope it wasn't too boring, but without further ado, let's move on to the actual science and application here. So coming back to our plot here, we see enhanced extinction coefficient throughout the majority of 2022, certainly into 2023. And from our extinction ratio plot here, we expect to see large particles. So how big are they? Well, we ran the SAGE data through our algorithm here. And here I have potential temperature plotted against time. And this just helps level out some of that latitudinal variability that we saw previously. And in general, what we observe is that the mode radius is between 350 and 400 nanometers in this main plume that follows along here. And this tends to decrease in altitude with time. So these large particles are falling out. This is fully expected, of course. But what I think is really interesting about this plot is what's going on above those really big particles. We still have some big particles up here along this line. This comes out to about 25 kilometers or so. We'll see this on some subsequent slides. But these guys are just more or less hanging out at the same altitude throughout the previous year. So this indicates that the impact of Hunga Tonga may be longer term than some of us may have expected, perhaps extending into multiple years. I think that's a really interesting possibility. Using this information, I was able to find the maximum radius, so what's the biggest particle as a function of time here, and generally speaking, throughout the majority of 2022, we're within 350 to 400 nanometers until we hit about December or so, and it looks like we've reached an inflection point there where the particles may be getting a little bit bigger. I'm not sure about that. With some more data under our belt, we'll be able to determine perhaps what's going on there, if this is a real trend or not, but it certainly appears to be that way at this moment. continuing on, I found the altitude where these biggest particles were manifest. And we start off here early in the year at 25 kilometers, and then we see this decrease throughout the rest of 2022 until we bottom out at about 15 kilometers. We continue to oscillate back and forth between 15 and 20 kilometers. This is likely some latitudinal variability that we see manifest here, but the largest particles have undergone an overall approximately 10 kilometer drop over the past year. And using this information, I calculated sedimentation rates broken up by latitude bin, where in the tropics, we see the slowest rate of descent of about 0.1 millimeters per second. And then at the highest latitude, we see the fastest rate of descent, 0.32 millimeters per second. But again, generally speaking, we're within approximately 0.2 to 0.25 millimeters per second, which is in rough agreement with Sergei Kaikin's estimate using Calliope data. All right, looking at our data here in a slightly different format, these are zonal monthly medians, and we see that early in 2022, the aerosol layer was pretty tightly grouped, centered around 25 kilometers, just offset from the equator. And again, the largest particles were about 350 to 400 nanometers. And as time goes on, these plots are approximately 3-month intervals. We see the largest particles slowly descending to lower altitudes and slowly going to higher latitudes, further and further south, until about in March of 2023, we see some of our largest particles down at about 12, 13 kilometers, all the way at 60 degrees south. And again, here, this last plot shows quite nicely the separation between our biggest particles at about 20 kilometers and these residual, big but not the biggest particles at about 25 kilometers, some of them extending up all the way almost to 30 kilometers. So this has quite an altitude spread here, and again indicates that these smaller particles will likely persist for quite some time to come. Another aspect of this plot that I think is really interesting is what's going on in the northern hemisphere in March of 2023. We're seeing the bleed over of some of these enhanced particles all the way up to about 50 degrees north. That's where the SAGE record stops, and it stops quite abruptly. So again, I fully expect to see these enhanced particles going even higher in latitude than that. So again, despite the relatively modest sulfur dioxide injection that we saw from Hunga Tonga, it looks like this may have a longer term and a longer term impact that isn't just in the southern hemisphere, but global as well. Okay, looking at a few individual profiles. Here, this is the extinction profiles for 3 SAGE wavelengths, the 448, 755, and 1.5 micron channels. And you'll see that there are 2 distinct peaks within this plot, one here that starts at about 21 kilometers, centered at about 22, and then one up here at about 24 to 25 kilometers. And I note here that the measurement uncertainty of the 1.5 micron channel at that altitude was a bit high, which does not play nicely with our algorithms. So that causes all sorts of spread in the solution space. So we're going to ignore that. We're going to just pretend that that peak does not even exist. Instead, we're going to look at the peak that occurs at about 24 kilometers. So looking at our mode radius estimate here, we see that that peak corresponds to a mode radius of approximately 350 nanometers. This is in good agreement with estimates from other groups. We haven't looked at the distribution width or surface area density or volume density estimates yet, but those are presented here. And the distribution width is showing a decrease as compared to what we expect for background conditions. I mean, we know this isn't background conditions, but it is a decrease from what we expect. Normally, background conditions are about 1.5 to 1.6. So if you had to pick a number, 1.5 would be perfectly fine. There's a lot of variability in that, but that's a good estimate. But here we're seeing a distribution width of about 1.25. So this is a substantial decrease. The particles are larger and they're within a more narrow distribution. For the surface area density and volume density, we see comparable increases as we might expect. And then the effective radius is estimated at 425 nanometers. And I point out that the POPs estimate, which is a particle counter, balloon-borne particle counter, estimated that the effective radius is 460 nanometers. This was provided by Troy Thornberry and Lizzie Asher's group at NOAA. This wasn't an exact coincidence, but this was pretty close, and the agreement is quite good here. So we have good confidence in that estimate. It's good to have that validation for that estimate. Now, one thing we proposed to do was to provide confidence intervals for these estimates, and that is shown here. This is the 90% confidence interval relative to the median. So what I mean by that is the confidence interval has an upper and lower boundaries. Just divide that by the median. You put it on a relative scale, so it gives us something that's more relatable, so we can say, oh yeah, that's like, plus minus 10%, plus minus 20%, et cetera. Now, you might not be able to see these lines. They're drawn quite thinly, but these lines in the middle here are the plus or minus 10%, plus minus 20% lines, just provided as guides to the eye. And what we see for our mode radius estimate at 24 kilometers right here is that the 90% confidence interval is within 10% of that median value. We see similar behavior for the distribution width at that altitude and the surface area density and volume density. These are higher order moments, so we expect those to be quite good, as is the effective radius. And what this allows us to do effectively is to say that we're 90% confident that our PSD estimates at this altitude are within 10% of the median, which I think is a really powerful statement to make. Now, you might be asking yourself, did you see any other events in this data? Did you run all the stage record through that? I'm glad you asked, because I did. So this is the southern hemisphere again, and we see all of the major events over the past 6 years. We see the impact of Ombay and Ulawan, the Australian New Year fire. We see really large particles from that, and Le Soufriere bleeding over, and then, of course, Hunga Tonga dominating the rest of the record. And what's interesting about this plot is that for these smaller events, such as Ombay and Ulawan, we're not seeing larger particles, we're seeing smaller particles. Now, I really wish we could say that we're the first to see this, but unfortunately, Felix Rana and Christian von Savigny beat us to this, and they have a very nice paper currently under review in, I think, ACP. It's either ACP or AMT. Look at both of them. Anyway, so in general, this is unexpected behavior of getting these smaller particle sizes. So we don't really know why this happens or how this happens. This is something that it's a new topic that is going to require further investigation. But we're not the only ones to see this. This is corroborated by other groups. Moving to the northern hemisphere, likewise, we see smaller particles from some of these smaller events. We see Ombay and Ulawan, of course, in the northern hemisphere. Those moved northwards, as Corinna Kloss described in one of her papers. And then, of course, we see Le Soufriere, and then Hunga Tonga bleeding over into the northern hemisphere with its large particles. So, in summary, the preliminary results that we have from the Hunga Tonga time period are encouraging, certainly encouraging. We see enhanced particle sizes in excess of 400 nanometers from this event, and this is in good agreement with the POPs record. We see decreased distribution widths, which again is expected, so this is comforting to see. And we observe other volcanic activity that showed particle size decreases. And with that, I wrap up my talk, and I hope I didn't talk too fast, but I gladly take any questions.